Hey you guys, here's our second installment of our nuclear chemistry videos over the PowerPoint slides for this chapter. Again, we're still looking at the strawberries and we are still looking at the sun. We are going to hopefully get to some of that today. So remember fusion and remember irradiating strawberries to make them last longer. So let's talk about nuclear transmutation. Nuclear transmutation is a process in which you have an element that is bombarded with small particles and then changes into something else and another small particle. This is kind of your template for nuclear transmutation. Nucleus, usually not that big, but it can be, plus a small particle to give a different nucleus and another small particle. These are some examples of transmutation reactions. So when you do fun sheet question number 1, you're asked, is this a transmutation reaction? If you see this sort of template, then yes, it is. Here's another example of nitrogen 14 going to carbon 11. And these transmutation reactions can be caused within these what's called cyclotrons, where you have a target, and on this target is usually some sort of atom. It can be one of these atoms, and you take a proton or a small particle and you zip it around as fast as you can get it to go, and then you hit the target. And when you hit the target, which contains any one of these elements, that you can convert it to something else. So I guess we would be seeing some other radiation in the form of these small particles being given off during that time. Here's a picture of the Large Hadron Collider, and it's under the ground, and it's in Switzerland. CERN is what it's called. It's the I can't remember what CERN stands for. I'll have to look that one up. But anyway, it's huge, and I have a video for you that I'll post for you about CERN and what they do there. This table 19.4, is something that you guys are going to work on for your fun sheet in your discussion. As looking at these transmutation reactions, you see a nucleus plus a small particle to give another nucleus and another small particle. Now, we don't always see that. For example, this neptunium does not have that being converted to plutonium. So I did ask you guys for your discussion board. I've assigned you some things to write the shorthand notation for these transmutation reactions. And that shorthand notation is a parenthesis with your nucleus plus the different particles and then another nucleus. So let's look at that type of symbolic nature for this transmutation reactions. So this one stands for nitrogen 14 plus an alpha particle. There's your alpha particle to create oxygen 17 and a proton. So as an example, to write the balanced reaction for this, so I'm asking you guys in your fun sheet to write the balanced reaction from this type of symbolic notation, and asking you to write the symbolic notation from the chemical reaction. But for this example, we have palladium 106 being bombarded with an alpha particle to form silver 109 and a proton. Another example of that would be iron. A D stands for deuterium, and recall that deuterium is a hydrogen nucleus. So there you have it there. What about gamma radiation? I wanted to bring this up because you don't see this. Your book doesn't talk about it that much, but anyway, a lot of times gamma radiation, which is a symbol gamma, and in our radioactive equations, we would have a 0 and a 0. And because it doesn't have mass or anything like that, it does not change the identity of the elements like we see here, but it is given off in a radioactive decay. But when you include it as a product, it doesn't change anything, but it is radiation being given off. And it's very dangerous, destructive radiation because it has a very short wavelength. So if you see that in your fun sheet questions about these types of things like these shorthand symbolic notations, sometimes you'll see a gamma in here, and that gamma just means it's a product, and your numbers that you would put here are 0 and 0. So let me rewrite that. That's a gamma. Not very good, I know, plus a 0 and a 0. So your fun sheet problem 11, for the discussion, post your assigned symbolic transmutation to chemical reaction or chemical equation to symbolic notation, and you'll see your assignments on the discussion board. And then we have number 12 on the fun sheet. Is alchemy real? It's kind of an interesting question where we want to convert mercury 198 to gold 198. So mercury 98 going to gold 198. How can we do that with the transmutation? So I ask you guys to think about that and post your answer. I found two ways, but one way is kind of not a transmutation because it only has two products, I mean, two reactants and one product. So anyway, I'll let you play with that, and I look forward to see what you post on that. Now let's go on to nuclear fission. Nuclear fission. Now there's a chain reaction, but what is fission? Nuclear chain reaction is self-sustaining sequence of fission reactions. But in order to get that self-sustaining chain reaction, you need to reach critical mass. So critical mass is where you end up having enough of these nuclei together in a small enough area that all the electrons that are given off during these fission reactions hit another nucleus and cause another fissioning. And when it causes another fissioning, you see energy being given off. And all that energy adds up, and you can get a big boom out of that. So this would be energy right here, and then this would be energy right here, and so on. Now this nuclear binding energies, we did talk about this earlier, and we actually calculated some things, but if you check this out, you'll see that the sum of these two is less than the original binding energy of the uranium. And that's where we get the energy coming off during this fission reaction, plus, of course, those neutrons that are traveling at pretty close to the speed of light. Maybe not the speed of light, but they're going pretty fast. And these neutrons are very dangerous radiation. They can actually go through human tissue or lots of things. They can go through concrete and end up breaking bonds. And then the person is, of course, not feeling too well. Keep on going with nuclear fission. So when nuclear fission occurs, a neutron hits a uranium nucleus, causes it to feel unstable, and then it fissions into those smaller products. It doesn't have to be these. I think you get a mixture of all different ones, but strontium and xenon are quite common. So for uranium-235, there it is again, it's just showing the energy and the number of neutrons. So for our energy, then if we were actually going to convert or actually calculate the amount of energy that's created from this process, we would use that E equals the mass defect times C squared. And if you actually do that, you get for uranium-235, you get this 3.3 times 10 to the negative 11 joules, but that's only one atom. So of course, we'll never fission just one atom. If we fission a joule of atoms, we get 2 times 10 to the 13th per mole of uranium-235. So you can see that's pretty large. A combustion of 1 ton of coal is only 5 times 10 to the 7th joules. So you can see why there's such a large difference and why nuclear power gives you a lot more energy to create electricity than coal. So how is this energy released? That movie clip we're going to look at here, and the movie clip is going to show some energy release. So let's go on and keep on going with nuclear fission. I have Who's That? That's just now. Hopefully that link, that movie clip you just saw, gave you a peek into the seriousness of nuclear experimentation. So I have some links out there for you, and I ask you to go look up those criticality incidents and see what happened. That was based on a true story that a man was using that screwdriver, and that broke, and then he flipped it off with his hand, and they have some gruesome pictures of what happened to him after that. So let's keep on talking about nuclear fission. When nuclear fission occurs, fissioning occurs, and you see these strontium and xenon nuclei that we saw on the previous slide, and this is almost like a mass spectrometer. See this? Where a mass spectrometer picked up these peaks and gave the mass of those isotopes. But I think there's quite a few of them in here. These are just the main ones. Let's talk about an atomic bomb. An atomic bomb was created for a big, huge explosion in a small mass. And the atomic bomb was created out of uranium-235. I have a picture here of one of the buildings that was left after one of the bombings in Japan in World War II. This building is actually still there. They made it into like a museum or something like that. So in order for an atomic explosion to occur, that critical mass must be achieved. So for your question number 14 and on the discussion, I'm asking you to explain how an atomic bomb works, just in your own words, in a couple sentences, and include an image that you find interesting. It can be an image like one of these things up here. and it's used in development or testing. Talk about the isotope that's used, hint, hint, right? We see it right up here, and write the nuclear reaction that occurs during that explosion. And then to do a quick calculation, how much energy would be liberated if an atomic bomb contained this much of that isotope. So I pointed you to page 872 for energy released from uranium undergoing fission. So let's talk about a nuclear reactor. A nuclear reactor is using nuclear energy that creates heat. I mean, a nuclear equation or reaction creates a lot of energy, which can be translated into heat. So in a nuclear reactor, you see there are control rods in here, and there's also fuel rods. And as those fuel rods are undergoing the chemical reaction or nuclear reaction, they create heat. And that heat heats this liquid that's inside here, that's red, and it circulates. And as it circulates, it heats water. So this is just a fancy steam engine. We really haven't gotten away from using steam as a power source, which is kind of nice, I guess, because steam can just be recondensed back to water. And that's what you see down here in the condenser. And then as the turbine is turned by the steam, the generator is turned. And remember, you can use a generator to generate an electric current through wires, and then it powers cities with electricity. This is a picture of the core and how it glows blue. If you remember that fun sheet question that talks about a blue glow. And then this is what your fuel looks like, this uranium oxide. In the core, there are control rods. The control rods are used to control things by absorbing neutrons, because recall that a neutron hits a uranium nucleus, which causes it to fission and give off the energy. So if you can block the neutrons, then you can stop that from occurring. So when this absorbs the neutron, you'll see there's that gamma that I was talking about before, gamma 00, and that is a form of radiation, gamma rays, which are given off during this process of neutron absorption. Boron is also used as a neutron absorber, and alpha particles are given off. So this looks like a lot like a transmutation reaction, both of them. Different types of reactors. There's one called heavy water reactors. They use heavy water, which is D2O instead of H2O as the moderator. That means fewer neutrons are absorbed, so the uranium does not have to be enriched. Fewer neutrons are absorbed. So I guess regular water absorbs a lot more neutrons. But see, this is very expensive and difficult to produce, because remember, hydrogen isotope 1,1 is 99.99% of available hydrogen. Deuterium, it's out there, and it's the hydrogen isotope of 2,1, but it's really hard to create, and it takes a lot of energy, and that's why Canada here has been able to use these, because they have many dams for the hydroelectric power to make a D2O. I'm not even sure how they make a D2O. A breeder reactor produces more fissionable material than it uses, and plutonium is made, which can be used for another reactor, and that's pretty expensive to create this type of reactor. Let's go on to nuclear fusion. Nuclear fusion is the opposite of fission. That's what's happening in the sun. In a fusion reaction, you see two deuteriums coming together to make a tritium. These are deuteriums to make a tritium and a protium. And there's a good bit of energy released for that reaction. This has got to be on a per atom basis. This is a tritium and a deuterium reacting together to make a helium and a neutron, and that gives off a good bit of energy. These are all fusion reactions which give off a good bit of energy. So here's lithium, and notice how small these are. These are all really small. Small nuclei fused together to make this. I don't think they can fuse any larger, because remember, when you get to such large nuclei, they become unstable. Fusion is kind of a pipe dream to a certain extent of trying to figure out, from what I know, and I don't know very much about it, of how you could harness the energy given off by fusion reactions to do just like we do in nuclear power plants, but the products you see here are much less dangerous as far as nuclear radioactivity is concerned. So a few things have been tried in this tokamak, magnetic plasma containment or confinement, because anytime this gets so hot that anytime it touches anything, it just melts it. So trying to figure out how to contain such a reaction when it gets that hot. has been a challenge. Laser, your book talks about laser confinement, and that's what this is. They're using laser to cause this fusion reaction right here. So it's not touching anything to melt it. The hydrogen bomb is an application, if you will, of the fusion reaction. And to get a fusion reaction started, you have to, and it's uncontrolled, mind you, you have to start it with a fission reaction because a fission reaction gets very hot. So then it can start the fusion reaction, and then that will give off that huge amount of energy that you're seeing over here. A lot of this was tested in the Pacific after World War II in the 50s and 60s and so on, as thermonuclear weapons were being developed. I wonder what happened to all the fish and everything and all the wildlife underneath there. Maybe there wasn't too much. But as far as lithium atoms and deuterium, see again, here's your fission reaction. And there's another fission reaction. Sorry, fusion. These are both fusion. I take it back. These are all fusion. So for your fun sheet question 15, I'm asking you to just explain how a hydrogen bomb works. You can read your book for that, and to go out and look for an image that you find interesting about the hydrogen bomb. Give the isotopes involved. And believe it or not, this type of bomb is still being tested by North Korea specifically. And so go out and Google North Korea hydrogen bomb 2020 and read about the ongoing insanity. It seems odd that people would still think they needed to do this, but apparently they do. And to this day, Japan is still having what they call it, bomb drills, where they set off a siren and then they all hide under their desks like World War II. So I don't know. Go look that up and see what you can find and post something to the discussion board.